Hi everyone. Today we're talking about the conservation of rotational kinetic energy. This is going to follow all the similar rules we used last semester, or was that chapter 7 and 8, when we talked about conservation of energy. Now we're just going to include rotational energy into all of those conservation problems, right? So number 1 says we have a uniform rod of mass m and length L. What and where is the rod's maximum angular speed if released from rest? So we know that as that rod swings, okay, it is going to have acceleration as it swings here, but then as it swings up, that would be negative acceleration, right? So we know that right here in its vertical position, that is where it's going to have its maximum angular speed, right? So let's find out what that is. Okay, here we will use conservation of energy. Okay, we'll get a COE going. We will use, okay, we'll say that it starts at UG naught plus K naught equals UGF plus KF. Okay? However, we will say that its final position is it's 0 for ZPL. Okay? And we'll say that initially it starts at rest. So this will simplify down to UG naught equals KF. Okay. Now we have mass M and length L. So we will say we've got mgh equals 1/2. Now this isn't going to be mv squared. This is going to be I omega squared. Okay. Now we also need to establish what is the height here. Well, we need to remember that we are going to use the center mass for finding the angular speed. Okay, that is because that is where gravity is going to be exerting its force, and we are talking about gravitational potential energy, right? So when we say that this guy swings down, right, what is the change in height? That change in height will be L/2, or the radius of the rod. So we'll have that out here, right? H equals L/2. And we want omega, right? Now, the I of this, okay, what is our moment of inertia? Our moment of inertia would be mr squared over 3, right? Because we have, let's see, we have a rod rotating about its end, right? So let's see, if we're going to stick with R for that, we'll stick with R for H as well, so that we've got a common variable there. So we've got mgr equals 1/2 times mr squared over 3 times omega squared, right? So we can see right off the bat that those m's will cancel. 1r will cancel. So let's simplify this, right? We've got, we'll multiply that 1/2 over, so you got 2g. You multiply the 2 over, multiply the 3 over also, so you've got 6 6g divided by r equals omega squared. Yeah, that's right. So then we will have the square root of 6g over r will equal omega. Yeah. Now, if you have that in terms of L, remember r is L/2. So that would also equal the square root of 3g over L if you incorporate the 2. So 2 different ways to solve that one, right? But here, that's where we used our rotational kinetic, right? Rotational kinetic is right here, 1/2 I omega squared. So we were able to find the omega here without using torque and using I omega. We used 1/2 I omega squared to find that. Now, for part 2, ask calculate the linear speed of the center of mass and at the end of the rod. So to find the linear speed, right, Right, we have V equals omega times the radius. And we just established that our omega is the square root of 6g over r. Since we're going to use r for this, I'll keep that in terms of r. Now we want the velocity at the center of mass. Okay, so we've got v equals omega. The center of mass for that would be the radius would be r, right? L over 2. So you've got r for that. Then the velocity, so that's center mass. Then here you have the end. Okay, velocity at the end, you'd have omega times 2r. So right off the bat, you can see that the velocities are going to be half or double, right? The velocity at the center of mass is half at the end of the rod, and the velocity at the end of the rod is double the velocity at the center of mass. Now we will move on to summation of energy or summation of torque. So here mass 2 is greater than mass 1, and they are connected by a massless string over a pulley of radius r and moment of inertia I about its axis of rotation. Number 1 says calculate the linear speed of m2 after descending a distance h, and part 2 says calculate the angular speed of the pulley at the time. So our big clue here is going to be that there is a distance h. When there is a change in height, you probably want to use conservation of energy. That's just a kind of a clue that you have there, right? So we want to look at the linear speed of m2. So we will look at the entire system, right? We'll look at UG1 naught plus UG2 naught. The pulley is not going to move, and everything is at rest. Okay, so everything's at rest. Then you have UG1 final, UG2 final. Then everyone has a kinetic energy, right? You've got K1, you've got K2, and you've got the, rotational for the pulley. Now let's start establishing what is going to be our ZPLs. We've already established one. The kinetic energies are in the initial case are at rest. So M1 is at its lowest point initially, so we'll call that its ZPL. M2 is at its lowest point finally, so we'll call that its ZPL. So if we rewrite this problem, you've got UG2 equals UG1 plus K1 plus K2 plus KR. Okay. Now, if we want the linear speed of M2, that means that we are trying to break this apart into its core components, 1/2 mv squared, and we'll solve for v. So first, let's isolate. Now let's get it all in component form first. So UG2 will be M2GH, UG1 would be M1GH, right? You can see that they're both going to move the same distance h. Right? So we can keep that consistent. And here we have 1/2 M1 V1 squared plus 1/2 M2 V2 squared plus 1/2. Here we have to use I omega squared. Now, another thing we want to recognize is that V1 and V2 are going to equal each other. Since they are attached by a string, we assume the string doesn't slip as it moves over the pulley, so we can establish that V1 equals V2, so we will actually remove the identifiers there, and we will just solve for that V. Now, we also want this in terms of linear speed, so we're actually going to take out omega, and we'll say that omega is V over R, right? So we're actually going to get rid of that and solve for that V as well. So we've got a V squared there also. So let's rewrite this. So you got M2GH equals M1GH plus, I'm actually going to factor out that V squared automatically. We've got m1 over 2, you got m2 over 2, and then you have I over 2r squared. All right. Yeah, if that's v over r squared, then yeah, you have I over 2r squared. Okay. And remember, I over r squared is kind of like saying you've got mass, right? Because if I is mr squared, I over r squared is going to give you the mass, right? Making this assumption here. So I over r squared kind of represents the mass of the object. So you can see here, all of the masses are divided by 2. M is divided by 2, r divided by 2, and I over r squared also divided by 2. Now let's solve for that velocity. Let's see, we have m2gh minus m1gh divided by those masses, m1 over 2 plus m2 over 2 plus I over 2 r squared. And that will equal v squared. So then to get your answer for linear velocity, you would take your square root. So get rid of that, and you would take the square root of all of that to get your velocity. Right? So that's how that's going to work. And you can use that to find linear velocity also, right? We used it to find angular velocity, right? But now we're going to show that you can use that for linear as well. Now we also want to calculate the angular speed of the pulley at that time, right? So this is our answer to part 1. How do we find the, the angular speed of the pulley? So we want omega p, right? So if we wanted to do that, we would have to show that omega squared is v over r squared, right? Omega is v over r. So if that's the velocity, right, you would just divide the entire thing by the radius, which would look ugly, right? So the omega of the pulley, we can assume, right, that everywhere that, so M1, M2, and the outer radius of the pulley, okay, all traveling at v. Okay, velocity of the pulley, velocity 1, velocity 2. We can actually make that assumption because that string is taut, doesn't have any slack, it doesn't break, right? So here you would have, I would honestly do it in 1 over r instead of some crazy fraction. 1 over r times m2gh minus m1gh divided by m1 over 2 plus m2 over 2 plus I over 2r squared. And that is how we will find omega, right? That's from the fundamental bridge equation, v is omega r. So that right there gets our job done, right? So that's how we can do that. Now, if we had numbers, we would actually be able to just take the velocity value, just divide it by the radius of the pulley, and you'd be done, instead of having that mess of variables. But we didn't get values, so we get to play with variables. Okay, last problem, a toughie with energy involved. So this one does get pretty complicated. We have a dense, thin cylindrical rod that you can see on the right. It is 24 centimeters long with a mass of 1.2 kilograms. There's also a ball with a diameter of 8 centimeters and a mass of 20 kilograms attached at the end of the rod. The system starts vertical at rest with the ball at the top and the apparatus pivots at the bottom of the rod. So let's get these givens first. Okay, the length is 24 centimeters, and I'm going to put that in meters. I'm also going to use a different color. So length is 0.24 meters. Mass, the rod is 1.2 kilograms. Diameter of the sphere is 8 centimeters. And the mass of the sphere is 20 kilograms. We also want the moment of inertia of the rod. That would be mr squared over 3. And the moment of inertia of the sphere, that would be, oh no, we won't be able to do that because the moment of inertia of the sphere is going to be complicated. So we'll actually save that for later. We're going to go over that in a minute. We'll have to use the parallel axis theorem to do that. But I guess I can leave that there and show that we will need that. Now, it asks how much kinetic energy is there after a 90-degree fall. Okay, so we are pivoting about that point down here. We're going to fall to 90 degrees, right? Next, we have, so kinetic energy. Then we want to know what is the angular speed of the rod and ball. Now remember, angular speed is the same throughout an entire rotating radius. So if we assume that that entire system is a rotating radius or a rotating system, we can show that the entire system rotates with the same angular speed. Then letter C, the linear speed of the center of mass of the ball. So remember, linear speed is going to depend on where along that radius you're looking. So let's start with kinetic energy after a 90-degree fall. So we want just plain kinetic energy. So we'll use a COE. Okay, we have the potential energy of the rod plus the potential energy of the sphere. And that will equal pure kinetic energy, because we'll say that UGR final and UGS final, we'll call those the ZPLs, right? We'll say that that is at height 0. Now, for the rest of this, this is going to get a little complicated, something that we haven't done before. Now, if you have MRGH plus MSGH, those heights are going to be different. So we have to look at what kind of height change are we having here. And remember, that's at the center of mass. So for the rod, okay, its center of mass is right here. So that H for the rod would be L over 2. But for the ball on the end, for the sphere, that height for the sphere, we would have to take the full length of the rod plus the radius. So you'll have L plus R for the ball. So we'll have to actually divide that diameter by 2 to use that. So we've got mass of the rod times G times L over 2 plus mass of the sphere G times L plus R. And that equals the kinetic energy of the system, right? That is, we can separate the kinetic energy of the rod and kinetic energy of the sphere, but it just asks for kinetic energy. How much kinetic energy is there? So we got off the hook there. So let's put in our values. Excuse me. So we've got 1.2 kilograms, gravity 9.81. The length divided by 2 would be 0.12 meters. Mass of the sphere is 20. G is 9.81. Then you've got the length plus the radius. So the length is 0.24. The radius wouldn't be 8 centimeters, it'd be 4. So we'd have 28 centimeters. So you got 0.28 there. That will give you your kinetic energy. And once you plug all of that in, you would get 56.4 joules for your kinetic energy. So that's how much kinetic energy it has after it has done its rotating. Now for part 2, part 2 asked us, what is the angular speed of the rod and the ball? Now remember, both of them are going to have the same angular speed, so that's why we can do this way. But to do this, we will say that the kinetic energy of the system equals 1/2 I omega squared. All right, so the moment of inertia, the total moment of inertia is going to be different here because we're going to have to take the moment of inertia of the rod plus the moment of inertia of the sphere, and the sphere is going to get a little complicated. Okay? So when we look at the sphere being rotated, right, with that moment of inertia, we're actually going to consider the mass of the rod in with the mass of the sphere. So when we consider the mass of the rod being rotated and the mass of the sphere being rotated, we're actually going to consider both of those masses as if they were in the sphere. So for the moment of inertia of the sphere, we will use total mass, which will be 21.2 kilograms, not 20 kilograms. So moment of inertia of the sphere, we're going to use the parallel axis theorem. You've got 2/5 mr squared plus md squared. And that d is going to be L plus r. That's the distance from the pivot up to the center of mass of the ball, of the sphere. So that will be L plus r squared. But again, new mass. So let's get all of that written out. That is 2/5 times 21.2. Radius would be 0.04 squared plus 21.2 times, 21.2 times 0.28 squared. Yeah. All right. And when you put that in your calculator, I got 1.676. 1.676 kilogram meters squared. Moment of inertia of the rod, that will be ml squared over 3, right? Yeah, ml squared over 3. Not mr squared, ml squared over 3. So you've got the mass of 1.2. The length would be 0.24 squared. Divide that by 3. That is 0.023. Kilogram meters squared. So we will add those up. I got 1.699. Okay, 1.699 kilogram meters squared. Now we've got to get the, that's all just to get the angular velocity here, right? So to get angular velocity, we'll take 2 times the kinetic energy divided by I. Oops. Omega squared is 2 kinetic energy divided by the moment of inertia. So, and then we'll square root that to get rid of the square. So you take, the kinetic energy was what, 56.4? Take the square root of 2 times 56.4 divided by 1.699. And I get 8.15. 8.15, and that will be seconds inverse, right? Radians per second as you read it. So that's how we can find the omega, right? But this system complicated. All right, last, what is the linear speed of the center of mass of the ball? So this part is going to be a little bit easier. Here we have V equals omega R. We already know what omega is, but what is the R from the pivot from the axis of rotation to the center mass of the ball? That would be L plus R, which we've used before, 0.28 meters, right? So that would be velocity equals, what do we have, 8.15. 8.15 seconds inverse times 0.28 meters. I got 2.28. Velocity is 2.28 meters per per second. Right? All right, so that is what we're going to stop with on our conservation of rotational kinetic energy. All we did is use rotating systems and incorporate kinetic energy of the rotation instead of just linear kinetic energy. And here we even discussed how that rotational kinetic energy, it just goes right in smoothly with the linear kinetic energies for a conservation of energy problem. In our next video, we will then finish up chapter 10 with one more lesson.